Hey everyone, welcome back. If you're gearing up for your A-level exams and really need to lock in those critical marks on system architecture, you've landed in exactly the right place. Today's explainer is a dedicated no-nonsense revision bootcamp. We're going to completely strip down the computer's boot process and system software into clear, super memorable concepts. Honestly, no fluff here, just the high-yield stuff you absolutely need to master. So are you ready to test your recall? I'll be throwing questions at you throughout this whole explainer, so you gotta stay sharp. Get those mental gears turning, because we're going straight to the bare metal.
Here's our game plan for today's study session. We're hitting 6 key areas: booting types, the step-by-step boot process, firmware, including BIOS and UEFI, post-beep codes, the software hierarchy, and finally, core OS functions. Let's get right into it.
All right, kicking things off with Section 1, booting types. Basically, how the machine actually wakes up.
Now, before we look at the definitions, I want to test you. Do you know the exact technical difference between a warm boot and a cold boot? Think about it for just a second. What state is the physical hardware actually in when you trigger either of these? Lock in your answer.
Okay, let's dive into this. A cold boot means you're starting the computer from a completely 100% powered off state. Think about turning on your PC first thing in the morning, right? Literally zero electricity was flowing. A warm boot, on the other hand, is restarting the computer without turning the power off completely. That's what happens when you just click restart in Windows or Mac OS. The power is continuously maintained to the physical components, but the software cycle completely resets. Now, why do we even care about this distinction for troubleshooting? Well, a cold boot actually clears out lingering, potentially buggy hardware states and totally flushes the RAM. So yeah, that classic IT advice of, have you tried turning it off and back on again? It actually works for a very technical reason.
While we're on the topic of boot speeds, here's a crucial definition that examiners absolutely love: the RAM drive. A RAM drive is essentially a virtual storage device that carves out a chunk of your system's RAM and just treats it like a hard drive. So ask yourself, why is a RAM drive so insanely fast? It's because it completely bypasses the physical, mechanical limitations and the slower data buses of traditional storage drives. By storing temporary files right there in the super fast volatile memory, the entire booting and operational process gets a massive speed boost.
Moving right along to Section 2, the boot process. Let's look at the exact step-by-step chronology of pushing that power button. The core sequence here is beautifully logical. First up, power on. Electricity flows from the power supply directly to the CPU, the RAM, the hard drive, and the motherboard. Now, the CPU wakes up, but honestly, it has no idea what to do yet. It immediately starts searching for instructions, specifically looking for the BIOS chip. Second, that BIOS or UEFI starts up to initialize the hardware. Third, we hit the post, the power-on self-test, which is this rapid-fire hardware check just to make sure all your essential devices are actually connected and working. Finally, once everything passes the post, the operating system is cleared to load into memory. Let's turn this into a bit of a narrative journey. Follow this path with me. After the power on, the BIOS, and the post phases we just talked about, the system hits a really critical fork in the road: the boot device selection. The motherboard looks for a bootable device. Maybe that's an SSD, a USB drive, or even a network location, all based on a priority order in your settings. Once it finds it, it reads the partition table. It'll either read the MBR for older BIOS systems or the GPT for newer UEFI systems, which is a vital distinction we'll cover in just a second. This partition table points directly to the bootloader, and that bootloader is the magical little piece of software that finally pushes the operating system kernel into your RAM, which eventually gets you to your login screen.
Okay, Section 3, firmware. Let's zoom in on BIOS and UEFI, the software that makes this whole sequence happen. Time for another quick active recall check. You've got physical, silicon hardware, and you've got digital, software operating systems. What exactly is the entity that bridges the gap between those two worlds?
Yep, it's firmware. Firmware contains the absolute fundamental instructions on how a specific hardware device should perform and communicate. Crucially, and you need to remember this for the exam, it is permanently or semi-permanently stored in non-volatile memory. Whenever you see non-volatile on a test paper, immediately think data that survives even when the power is pulled. Usually this is read-only memory, ROM, or modern flash memory that's literally soldered right onto the motherboard.
Over the years, this motherboard firmware has evolved in a big way. On one side, you have the classic BIOS, the basic input-output system. It's that older, clunky, text-based interface you have to navigate entirely with a keyboard. On the other side is UEFI, the Unified Extensible Firmware Interface. This is the modern, slick, graphical replacement that actually lets you use a mouse. Now, what's really fascinating here is the CMOS. Any settings you tweak in either of these interfaces, stuff like your boot priority or the system clock, they get saved to the CMOS memory. And that memory is kept alive by a tiny little coin cell battery right there on your motherboard, which ensures your custom settings aren't wiped out the second you unplug the PC.
So, the crucial point for your exam is understanding exactly how these two stack up technically. Let's run a quick scenario. If a client brings you a massive 4 terabyte hard drive, which firmware must you use to actually boot from it? Well, it has to be UEFI. Why? Because BIOS, which was developed way back in 1981, operates in 16-bit and uses the master boot record. That physically limits partition sizes to a maximum of 2 terabytes. UEFI, which arrived around 2002, runs in 32 or 64-bit modes, giving it access to way more memory, and it uses the GUID partition table, completely shattering that old 2 terabyte limit. Also, and this is a massive exam keyword, UEFI supports Secure Boot. Secure Boot is awesome because it physically prevents unauthorized operating systems or nasty rootkit malware from hijacking your system while it's trying to boot up.
All right, Section 4, Post-Beep Codes. Let's shift gears and play a rapid-fire hardware diagnostic game.
Imagine this. You press the power button, the screen stays pitch black, but you hear this. One long beep, followed by one short beep. Lock it in? What specific hardware failure is the computer complaining about?
If you guessed a memory or RAM error, you nailed it. The motherboard is basically screaming that it cannot find working system memory to load the OS into. If you get the specific error in an exam scenario, your very first troubleshooting step is going to be opening up the case and reseating the RAM sticks on the motherboard.
Okay, let's try another one. You hit the power button and you hear one long beep followed by 3 short beeps. What's the system trying to tell you this time?
That one is a video card or graphics error. It means the system literally cannot initialize the display adapter, which totally explains why your screen is blank. By the way, if you just hear one single standard short beep, take a breath. That simply means the post passed normally. The hardware check is totally complete, and the system is successfully moving on to the bootloader phase.
We've got the hardware powered up and fully tested. Awesome. Let's move to Section 5, Software Hierarchy.
Think of this like a building. Start at the very foundation. We have the bare metal, your actual hardware components like the CPU, memory, and your peripheral devices. Sitting directly on top of that bare metal is the system software, which is primarily your operating system. The OS acts as the great coordinator of everything. Then, resting right on top of the OS, you have your utility software and your application software, and that's the layer the human user actually interacts with. So, quick check for understanding here. Where do you think a device driver sits in this stack? Well, it's firmly in the system software layer, acting as a direct translator that bridges the gap between the OS and the hardware.
Now, zooming in on that system software layer, we have utilities. Think of utility software as your system's dedicated maintenance crew. For your exams, I want you to frame these as the 4 pillars of utilities. Let's test your recall with some real-world examples. Pillar 1, they improve computer performance. Think of a tool like Disk Defragmenter. Pillar 2, they protect the system from threats. That's your Windows Defender or your antivirus software. Pillar 3, they manage files and storage, like your file compression tools. And Pillar 4, they diagnose and fix system problems, like a standard disk cleanup utility. The key takeaway here? These aren't apps designed for you to write an essay or play a video game. They are dedicated tools built strictly to keep the computer itself healthy.
And that brings us to the grand finale, Section 6, OS Functions, the absolute powerhouse of the computer.
An operating system controls, coordinates, and manages literally everything. Let's break down its core functions, because this is a massive area for AILL questions. First, it provides user interfaces, translating raw binary into the graphical windows or command lines we actually understand. It ensures security and protection through user authentication and really strict file permissions. It executes application software, just making sure your programs run smoothly. It handles incredibly intense resource logistics, like memory management, which means aggressively assigning and freeing up RAM spaces so you can run multiple programs at once without them crashing into each other. It performs device and file management, figuring out how to talk to your printer or your mouse through drivers. And crucially, it handles system calls. Think of a system call like a waiter at a restaurant. Your application, the customer, cannot just barge into the kitchen, the bare hardware, and start cooking. That would be a massive security risk. Instead, the application has to make a system call to the operating system, our waiter, who safely goes to the hardware, gets exactly what is needed, and brings it back.
Which leaves us with this final, kind of provocative thought to wrap up our bootcamp. If the operating system didn't exist to provide this seamless virtual machine interface,
How could an application developer ever write a program that actually communicates with the bare metal of thousands of completely different hardware combinations? Think about it. Without an OS handling all the system calls, the memory, the drivers, it would be pure, unadulterated chaos. The OS is what brings order to that chaos. And with that, congratulations on crushing this ASL Revision Bootcamp explainer. Keep reviewing these concepts, visualize the flow in your head, and you are absolutely going to ace this section on your exam. Keep up the great work.